Okay, in today's lecture, we're going to discuss the concept of equilibrium. And we're now moving sort of out of kinetics in the past lectures into equilibrium. And kinetics is all about how fast a reaction happens, right? And in an overall reaction, A plus B goes to C plus D, right? Kinetics is about what is behind this arrow, okay? What are the mechanistic steps that actually get from reactants to products? Because it might not be that A and B collide and make C and D in one step. It might be more complicated. What is that complicated mechanistic process? How long does it take? That's kinetics. Equilibrium is more about where does it end up over long time scales. Okay, so let's look at an example. And what I want you to do here is sort of recall a concept from early on in our general chemistry course, vapor pressure. Okay, when you introduce a liquid to a container, right? Maybe there's a closed container down here, and ignore all this text for now. Okay, students love to read text and are missing the important points, so ignore all that for now. Okay, imagine I pour liquid into this container, right? And here's some liquid. Okay, some of the liquid, right, the molecules here, will have enough energy to detach from the other liquid's intermolecular forces, like a water hydrogen bonded to a water. Well, this water molecule has enough energy to leave that hydrogen bond, to break it, and go up into the gas phase. And so now up here is the gas phase. We have some waters up here. The pressure that these water molecules exert on the edge of this container is the vapor pressure, okay? And it's only the pressure that is exerted after equilibrium is reached. So we introduce this liquid, some of the molecules go up to the vapor phase, but later they come back down and re-enter, right? Nope, there we go, re-enter the liquid phase. So there's this constant leaving the liquid into the gas, re-entering the liquid from the gas, that is happening. But over long times, we establish what's called a dynamic equilibrium. Meaning stuff is still chaotic and happening. At all points in time, some waters are leaving the liquid phase, some waters are entering the liquid phase. But the rates of those two processes are equal and opposite. That is dynamic equilibrium. And instead of vapor pressure and molecules just transitioning between liquid and gas phase, we're now talking about a chemical reaction, okay? That has a dynamic equilibrium. So let's ignore now this vapor pressure example, right? And concentrate now on chemistry instead, right? And let's think about a reaction that happens N2O4, which is a colorless gas that dissociates into NO2 plus NO2. So the nitrogen-nitrogen bond breaks, and then you have two NO2 molecules from this N2O4. Now, NO2 is brown, N2O4 is colorless. Okay, and this is these NO2s are really dark brown, so dark that eventually, you wouldn't be able to see through a cloud of it. That's how dark it is. However, remember our vapor pressure, gas molecules can re-enter the liquid phase. If this was one directional, right? N2O4 just making NO2, then over long time scales, which is what's signified here, as we're speeding up the reaction, this is cold water, this is medium water, this is hot water, encouraging this forward reaction more and more, right? You could just wait much, much longer, but you can speed it up if you actually warm it up, right? This dissociation. As you go from cold to medium to hot, you're getting browner, right? But you would get dark brown, so dark you wouldn't even be able to see through the test tube if it went only in this singular direction to NO2. But what happens is, eventually, this cold water one will get this brown. This medium water one will get this brown as well. You can just see sort of the stages of the reaction happening. More and more N2O4 is falling apart. But eventually this hot one is meant to represent sort of long time scales or the end of the reaction. At the end of the reaction, it isn't only NO2. If it was, it would be so dark you can't see through it, okay? What has been reached here in this hot vessel or over long time scales is the fact that there is a dynamic equilibrium established, because what's happening actually at all times is as soon as one of these N2O4s falls apart and creates NO2s, those NO2s can recombine to make N2O4. right? Much like the liquid going up into the gas phase, well, the gas can re-enter the liquid phase. But over long time scales, there is a balance that is reached, an equilibrium, if you will. A chemical equilibrium then occurs when this reaction and its reverse, that's why there's a double arrow here, forward reaction, reverse reaction, when a reaction and its reverse reaction proceed at the same rate. So in the figure above, equilibrium is finally reached in this third picture as the gas remains this shade of brown over long times. Okay, so you put these three vials in. This one turns brown slow, this one turns brown a medium amount of time, and this one turns brown really, really fast, but stays this color brown, okay? It doesn't get so dark brown that you can't see through it, suggesting it's only NO2, but it gets this dark brown because it's a lot of NO2, but some N2O4, because some is recreated while the two NO2s come back together, okay? It's really conceptually important for us to understand at the molecular level, things are dynamic, okay? They're not very static. The microscopic world is crazy. Okay, so in a system at equilibrium, both the forward and reverse reactions are being carried out. That's why we write this double arrow. So sometimes you'll see it as I write it with literally like one arrow with two ends on it like that, poorly drawn, or you'll see it written as shown in this neater figure down there, sort of two half arrows forward and backwards. And, you know, technically speaking, every single chemical reaction is reversible. There's this, law of microscopic reversibility. If N2O4 falls apart to make NO2, well, NO2s can come together to make N2O4, okay? It's just, it might be very, very favored to go forward, or said another way, which we'll talk about later in this lecture or a future lecture, over long timescales, you might get mostly NO2 at the end. So, if over long times there's a few N2O4s left, but most of it is NO2, well, then you might approximate that by a single forward arrow, because basically all the N2O4 turns into NO2, but not exactly all of it. Okay, that's sort of an approximation. Instead, it's appropriate to use the double arrow. And a lot of what we're going to be talking about over this lecture and the future lectures in this module here are these reversible processes where things are a bit more balanced. Although technically all processes are reversible and have this two-way action to them. Now, let's consider this two-way action as two separate processes. And this is how we're going to build something called the equilibrium constant. So for the forward reaction, N2O4 falls apart, it decomposes into two NO2s, right? And hearkening back to kinetics, if this is a single step, we would write, well, the rate constant is K times the reactants, okay, to some exponent. And if we know the mechanism, that it's just a single N2O4 falling apart, which we do here, then it's to the first power and the one is implied. Okay, so that's our rate, K N2O4. For the reverse reaction, we can consider two NO2s bumping together to make N2O4. So the rate here, and if you're confused about kinetics, please go back and watch the videos on kinetics. Here, the rate law would look like this, NO2, and there's two of them bumping together, assuming this is the mechanism, which we're going to assume here. If it's the mechanism, then I can write the power, right? If I don't know the mechanism, I have to do experiments, analyze the data, come up with the mechanism. But here, knowing the reaction mechanism for this straightforward reaction already, we can write these two rate laws. For the forward, so I'll say this is forward, and the reverse, so I'll write this as K sub R for a reverse reaction. Right? And again, I'm going to assume here that these are elementary steps. Okay, so maybe I'll make that point here. Assume that this and this are the two elementary steps that make up the entire reaction, N2O4 reversible to two NO2s. Okay, so that's our reversible reaction here, and we're going to assume they're elementary steps. If they're elementary steps, we can write the rate laws. So having written those rate laws, right, we can think about, okay, let's just set up a beaker or a test tube and place in this just N2O4 and start our timer. Say go. What happens? Some of that N2O4 is going to decompose, right? And so the amount of N2O4 we start with, right, shown here in black at time 0. Okay, here's t equals 0. I don't know, here's t equals, right, 10 minutes or something. The N2O4 concentration starts decreasing, right? So you would label this point right here at time 0. You would label this the N2O4 concentration initially or at time 0. That's what that little knot or 0 means right there. It's a time equals 0. That's my initial concentration of N2O4. Okay, my initial concentration of NO2 is 0. We're not starting with any NO2. We're literally introducing N2O4 into a test tube and letting it decompose, hitting our stopwatch, go. So as the N2O4 falls apart, you see it's decreasing, it's decreasing, it's decreasing, and then it stops falling apart. But don't be fooled. This does not mean it stops falling apart, right? Go back to our initial example here of vapor pressure. Once the vapor pressure is established and there's an equilibrium, doesn't mean there's no longer liquid waters going to the gas phase. No, there's still liquid going to the gas phase. There's still NO2O4 decomposing to make NO2. It's just that it's happening at the same rate as the reverse process is happening. There's still gas phase re-entering the liquid phase. These, gas molecules are bumping around, always entering and leaving the liquid phase. It's chaotic. In the same way, this reaction is constantly happening. N2O4 is constantly decomposing into NO2. But as the concentration of NO2 here gets high enough, well, now with a lot more NO2 around in my test tube, they're going to find each other much more often. And there's going to be NO2s next to NO2s much more often. So they're going to combine much more often and remake N2O4. Right? So as the N2O4 is decomposing, as the NO2 is being created, more NO2s bump into each other and recreate N2O4, but there's still some N2O4 falling apart. But eventually, past this point or so, equilibrium is established. Okay, as the system approaches equilibrium, both the forward and reverse reactions are occurring. At equilibrium, the forward and reverse reactions are still occurring, but they're occurring at the same rate. Okay, so after this point right here or so, the rates are equal for the forward and the reverse process. Okay, so the amount of each reactant and product remains constant. It doesn't mean a given molecule of N2O4 never decomposes again. It just means if it does, somewhere else at that moment in time, two other NO2s come together to make N2O4. Okay, now at equilibrium, when these rates are equal, right? Here the rates are equal. The concentrations are leveled off and not changing. We can connect kinetics to thermodynamics and equilibrium here. Here are the kinetics. We know the rate laws for these processes. We wrote them down. At long times, once the equilibrium is achieved, these rates are equal. They're equal and opposite. That's what's shown out here. They're equal. They're opposite, meaning no N2O4 is net changing. The concentration isn't changing because every time one N2O4 falls apart, two NO2s somewhere else are recreating that N2O4. So we can set these two rate laws equal to one another, right? And now we can do some simple algebra, divide both sides by N2O4, collect our KRs, and now we have an expression that describes to other scientists where the reaction is going to wind up at long time scales, right? So we have a simple expression for what does it look like out here. Early on, it's chaotic. We need both rate laws to describe this section. But out here, it's easy, right? There's still dynamic stuff happening all the time, but the rates are equal out here. That allows us to set the two rates equal to one another and combine them, right? And we call this combination, we lump these two small k's together in a large K and call it KEQ, products over reactants. Okay, here that's NO2 to the second power over N2O4. Remember, this is for the overall reaction N2O4. Double arrow, 2 NO2s. So I take my products, NO2, and there's 2 of them. NO2 to the second power. Remember, these reaction orders, these exponents, are how many things are colliding. And again, we're assuming this is an elementary process, or we know the elementary steps here, which means we can write the rate laws, which means we can rearrange the rate laws for this simple equilibrium expression. So 2 NO2s, that's our product, NO2 squared, over our reactants. There's only one of them, it's just N2O4, so that is our equilibrium constant. Okay, and so this is the important metric for where a reaction ends up. Over long time scales, how much product is there compared to reactant? We have a singular number at this temperature, it's the KEQ. It's not going to matter how much reactant I start with, the ratio at the end is going to be this same constant. No matter if I start with 1 mole per liter or 10 moles per liter or whatever you want to start with, this equilibrium constant at this temperature is going to be that constant. It's going to eventually get to here. So let's consider another equilibrium. This is the Haber process, right? Industrial preparation of ammonia, which is a feedstock for fertilizer and really helped feed the world in the early 1900s when this was discovered by Fritz Haber. Now, we can look at this reaction, okay, assuming this is an elementary process. Again, go back to our kinetics video. Elementary here means that this describes what molecules have to bump into or collide with one another to make the products. Okay, and it's not some more convoluted reaction that we have to break down into many mechanistic steps. Okay, so assuming this is elementary, our expression for K is just going to be our products raised to their power, NH3, to the second power, over our reactants multiplied by one another, so N2 to the first power, because there's a 1 implied out here in front of N2, times hydrogen to the third power, because there's a 3 out front of hydrogen here. Okay, and this is our equilibrium constant, shown at the bottom here, much neater so you can read it. And technically this is Kc, right? And it's Kc because it depends on concentrations, right? We'll also see that we have a Kp that depends on pressures. And which one you use depends on, well, the exact application or the problem you're trying to solve, and whether it's dependent on liquids and concentrations and aqueous solutions, or if it's gas phase, then it's probably going to be pressures. So we can write this more generally, whether it's for the N2O4 reaction we considered, or here for the for the Haber process, which we considered. We can generally write it like this. It's always products over reactants, and it's the products raised to their stoichiometric coefficients, right? So e to the power of, this could be a 2 or a 3 or a 1, whatever it is, it's raised to that power, over reactants, b to the small coefficient b, b to the power b, a to the power of a. It's always products over reactants, and this is Kc technically because there's concentrations. Remember, these brackets mean molarity and concentrations. Pressure is also proportional to concentration for gases. Think about PV equals nRT, so P equals N over V. That's a concentration. So concentration is proportional to pressure. You can write something quite similar. So really in our example of N2O4, which is a gas, falling apart to two NO2s, which are gases. It might be more appropriate to think of Kp, an equilibrium constant, with regard to pressures, because it might be easier in the gas phase to measure the pressure of one of the things than it is a concentration, which is typically reserved for the liquid phase, aqueous solutions. So this might be pressure of NO2 squared over pressure of N2O4. Okay, more generally for a reaction like this, okay, Kp would look like this. It's still always products raised to their stoichiometric coefficients over reactants to their stoichiometric coefficients. So let's do some practice here. Feel free to pause the video here and try yourself to write an expression for Kc for the reactions below. Otherwise, I'll go ahead and solve it. Pause the video here if you want to try for yourself first. Okay, Kc, maybe we'll separate this into A and B. For A, Kc, even though they're gases, it asks for concentration, so I'm going to write this as a concentration. It's always products. The product here is oxygen. The coefficient becomes my power. The reactant here is ozone, O3. That's my denominator, to its power, 2. And so for part A, the equilibrium over the concentration of O2. Sorry, the concentration of O2 cubed over the concentration of ozone squared. Okay, for part B, we're going to do the same thing. Concentration of NOCl over the concentration of NO times the concentration of Cl2. There are no exponents here, right? Because all of these are just ones. Oh, but I made a mistake, right? And the mistake here is I didn't actually check that my reaction is balanced. Okay, up here it was fine because there's 6 oxygens on each side, but this would be wrong, right? Because I'm going to need a 2 here to balance my chlorine. And I'm going to need a 2 here to balance my NO. So that means my NOCl must be squared and my NO must be squared. Okay, so that one can be a bit tricky because you might not realize, I should say, to balance it first. You see a reaction, you write products over reactants, done, but always make sure first to check that it's a balanced chemical reaction. So those are the expressions here for Kc. One last thing I'll mention here is that Kc or Kp okay, this is a star in your notes, have no units. Okay, they are unitless quantities, they are constants. And this is by convention. We'll learn in future lectures that, equilibrium constants or equilibrium concentrations or pressures, I should say, are referenced to some standard 1 molar or standard 1 atmosphere. So, the concentration units sort of get factored out as part of the process of making an equilibrium constant. But just assume for now that this Kc or a Kp, if we were asked to write that, would still be a dimensionless quantity, meaning there are no units. Okay? It comes down to a concept called activity, and we'll get to that perhaps in future lectures. For now, just remember Kc and Kp are unitless. For Kc, you use concentration. For Kp, you use the pressures at equilibrium. Don't use initial concentrations or initial pressures. It's over the long time scale. Once the kinetics has, finished, the reaction has sort of finished and ended up in an equilibrium, those are the concentrations or pressures you want to use, the ones after long time scales, after the reaction is done running. Okay, the initial concentrations don't matter. The system will eventually evolve towards and end up at an equilibrium in the end. So that'll do it for this lecture where we introduced equilibrium. Up next, we'll talk about the exact magnitude of the equilibrium constant and what that means, and reference it to another quantity like the equilibrium constant, not K, but Q. And we'll work from there into ice charts and ice tables as we learn how to quantify equilibrium problems further. But that'll do it for this lecture. See you next time.